Hello and welcome to this video podcast. In this podcast I'll look at Archimedes and specifically how he used the method of exhaustion to approximate the values of pi. So who was Archimedes? He was born around 290 BC and died in either 212 or 211 BC when Syracuse, the Sicilian city where he lived, was seized by the Romans. Many myths surround Archimedes. For example, he is credited with inventing several war machines. One war machine that he is said to have invented is the heat ray, which used mirrors and the light from the sun to cause Roman ships to burst into flames. By pointing the mirrors correctly, he could focus the sun's light on enemy ships. A scary weapon, but is it plausible? The weapon was tested in Greece in 1973, when 70 copper-coated mirrors were pointed at a plywood ship that was placed in the sea. The scientists testing this managed to get the ship to set on fire, although the ship was coated with tar. It seems highly unlikely that Archimedes did use mirrors as a weapon to set ships alight, because getting the ships to set on fire would have required the ships to be very still, and other methods of setting them on fire would have been easier and more reliable, for example, simply using flaming arrows. It could be possible that the mirrors were used to simply shine bright light at the soldiers, making it difficult for them to see. Some of his inventions are less likely to be myths, however. For example, a device known as the Archimedes screw. The screw was used to pump water. By rotating the handle, water at the bottom of the tube is picked up and carried up to the top by the spiral. Although best known for his inventions, Plutarch, born 46 AD in Greece, who wrote biographies of Roman emperors, described how Archimedes himself much preferred the study of theoretical maths, particularly geometry. This is highlighted by the fact that Archimedes requested that his tombstone have a sphere and circumscribed cylinder on it, referring to his famous proof that the volume and surface area of a sphere is equal to that of 2/3 its circumscribed cylinder. This fact was confirmed by Marcus Cicero, who discovered the gravestone around 150 years after Archimedes' death. Archimedes was killed during the siege at Syracuse when the city was taken. Although Archimedes helped defend Syracuse from the invading Romans, the attacking Roman commander, Marcellus, was said to be afflicted by his death, not wanting the man to have been killed. Because of this, it seems likely that Marcellus would have honoured Archimedes' wishes and allowed the inscription on his tomb. Archimedes proved his theorem by using the method of exhaustion. Let's take a look at what that actually is, and we'll see how he used this method to approximate pi. So how does the method of exhaustion work? The method of exhaustion is a method of working out an area by approximating it by the areas of a sequence of polygons. The idea is that by increasing the number of sides of the polygon, the area of the polygon becomes closer to the area of a circle. He approximated pi by finding an upper and a lower bound. Pi is the circumference of a circle divided by its diameter, so pi equals c over d. We can use the method of exhaustion to find out pi. Note that the method we will use here is different to the actual method of Archimedes, but the basic idea and the use of the method of exhaustion is the same. We put a regular polygon, in this case a hexagon, inside the circle. If we find the perimeter of the polygon and then divide it by d, we will get a number. As the polygon is inside the circle, we can tell that the perimeter of the polygon is definitely less than the circumference of the circle, and so the number we would get is definitely less than pi. So let's work that out. We take the radius of the circle to be 1. We know that the interior angle of a regular polygon is n minus 2 times 180 over n, where n is the number of sides of the polygon. We won't go into why this is true here. In this case, that number is 120 degrees. We can add a right angle triangle like this. So the interior angle is divided in half. Hence, the remaining angle of the triangle is 30 degrees. We can work out this this side of the triangle here, which we'll call x, by using the sine rule. We can plug in the detail and we get that sine 30 over x equals sine 90. We can rearrange this and we get x equals a half. We double this to find the length of the side of the polygon, which is 1. As the shape is six-sided, we times this by 6 to find the total perimeter of the polygon. We can now find a lower bound for pi. We take the perimeter and then divide it by the diameter, which is 2 as our radius was 1. So we've just shown that pi must be larger than 3, as we can see here. The perimeter of the polygon is 6, the diameter is 2, so when we divide it we get pi must be greater than 3. We can do this same method with all polygons with all numbers of sides. The interior angle is split, a right angle triangle can be made, and pi can be approximated. You can try this yourself with a different polygon. Try a pentagon. In general, to find a lower bound for pi, we can use this formula. N here is the number of the sides of the polygon we use. The higher the number this is, the closer the lower bound will be to pi itself. Similarly, we can place a regular polygon outside of the circle to get an answer that is definitely larger than pi. This works in a similar fashion, with the result of the perimeter of the larger hexagon when divided by the diameter, giving an upper bound for pi. In this case, pi is less than 2 root 3, which is about 3.4641. Using both bounds, we can approximate a value for pi by taking the average of them. Here we get an average of 3.23205. So by just placing the hexagon both inside and outside of a circle, we have come up with a crude approximation of pi. If we use polygons with a greater number of sides, the perimeters of these polygons will get closer to the circumference of the circle as the number of sides increase. So by using polygons of the larger order, we can get a better approximation of pi. This is the method of exhaustion at work. So let's see what happens when we use a larger regular polygon, for example a dodecagon, which is a 12-sided shape. This gives an approximation as pi as 3.160605. Archimedes did this with a 6-sided shape, a 12-sided shape, and continued doubling up until he got a 96-sided shape. Using 96 we get this answer here, which is a very good approximation. This is the approximation that Archimedes himself found. Using the general method we've been using so far, we can work out bounds of pi by using as many sided polygons as we want. So we plug in and say we want to use a 1,000-sided shape, we get this answer here. And we can even go up to 100,000. Put a polygon in with enough sides and you can get some very good approximations for pi indeed. And that concludes the podcast. Hope you've enjoyed it.